In this short video, we just put sort of everything together and come full circle on conformational analysis. And this is overall used to sort of try to predict how molecules often will react with other molecules or atoms, or how they will bind if they're binding to a certain substrate, or maybe even how they might crystallize, since a crystal lattice is formed by stacking of like-shaped molecules, similar shaped molecules. So there's all kinds of reasons why we want to understand conformational analysis and end up doing these sort of analyses of molecules. There was some of this in as far as the cyclohexane rings in Module 2, Video 3. So coming from there, we have a chair cyclohexane conformation. Remember the chair conformation. And in this case, it's a 1,3 di-substituted chair with methyl groups. Here we have what everyone now hopefully recognizes as a higher energy form. And we learned earlier because that has 1,3 diaxial interactions, which are interactions that lead to higher energy. Now we know also from the last video that this is a form of steric strain. So 1,3 diaxial interactions are steric strain due to the size of the methyl groups in this case. If we then do our ring flipping and get to where they're both equatorial, di-equatorial we would say, instead of diaxial, so di-equatorial. We're at a lower energy state. And up to now, we've just explained that with the fact that there are no 1,3 diaxial interactions to be accounted for. Let's do an analysis. So let's do our Newman projection analysis. First of all, we'll look at it from C2 to C1, so sort of in this direction here. Looking at it from C2 to C1, the left structure on top will look like this. Hopefully you can see how I got to that. Notice everything's staggered. The chair conformation makes all substituents staggered. And however, we have what we now know is termed gauche interactions. Gauche or gauche. There's one there and there's one there. So there's two gauche interactions. In the Newman projection, looking from C2 to C1 on the right upper structure, we only have the one gauche interaction. Notice we don't have another gauche interactions. So we're not really paying attention to protons. They hardly take up any space. So our Newman projection analysis, looking from C2 to C1, supports the fact that the left structure is higher in energy without having to refer to the diaxial interactions. Let's do another analysis looking at the Newman projection from C3 to C2. So sort of looking at it in this direction here. Okay, and we're going to go off the screen a little bit, but that looking from C3 to C2, on the left structures right here, we have, again, two gauche interactions. And on the right structure, we have, again, only one. So no matter how you look at it, whether you're just considering 1,3 diaxial interactions and steric strain, or if you're considering how many gauche interactions there are, which is basically torsional strain, right? So the ring can still flex, but for it to flex, for example, from moving this methyl closer to either of these positions will introduce torsional strain. So all these various kinds of strains, they all agree that the left structure is the higher energy structure. Now, some people say, oh, well, you showed us all these other different conformations of six-membered rings, like the ever-popular boat conformation, right? So I drew the boat. First I built a model of the boat conformation and then drew what I saw. It's a little bit tougher, but you can still make a Newman projection however you want. You can use this way of drawing, this style of projection, to analyze any structure you want, not just a chair conformation, but here's a boat conformation. And looking at these three bonds up front, we see them, well, the way it looked as I was looking at the model was that it was these three bonds up front. The two protons, and then this, where it connects to the rest of the ring. Then the atoms in back appeared like you see here. So you would say, okay, looking at it from C2 to C1, this boat conformation doesn't seem so bad. Everything's staggered. Yes, there are gauche interactions, but I don't see why the boat is so much higher in energy. Well, if we do the other analysis like we did above, looking at it from C3 to C2, now take a look. That's down here. And when I look at my model that I built from C3 to C2, everything is eclipsed. So above all, eclipsed forms are higher in energy, as we saw, even with simple ethane. So the boat conformation is higher in energy because of too much eclipsing all around. Really, it's on the sides of the boat. Both port and starboard sides of the boat have all eclipsed substituents. Now, just a little bit of a tip, a pitfall to avoid, something to avoid. So if I'm drawing a cyclohexane substituted like this, I draw it like this. This is perfectly correct. We're drawing it in this particular way to show it clearly. So we don't need the wedges and the hash marks when we're drawing it in this particular style of drawing, like for a chair. So do not use wedges and hash marks on a conformational style drawing. Now, if I am drawing it flat, and in fact you'll see it drawn this way most of the time, that's when you want to use the wedges and the hash marks, because that's telling us that it's up or down. But the drawing, the particular style of conformational structure drawing, that very clearly shows what's up and down. And so you don't need the wedges and the hash marks. It might even be confusing to put them in there. And that's the end of this shorter video. The next video will deal with some things really much more forward-looking into the next module. A quick survey of functional groups and the beginning of talking about reactivity in terms of electron movement.